After you calculate the diameter of the shaft, you just need to think also about the critical shaft speed. So this shaft is going to rotate, right? So the shaft, in this case, in our case, rotates. So it rotates with a specific RPM, okay? So we just want to make sure that this RPM that is less than what's called N critical, which is the critical speed of the shaft. What's wrong about the critical speed of the shaft? This is what we are going to learn. So we have here the operating speed of the shaft, and then we want to make sure that this operating speed of the shaft is far more less than or far more away from the critical speed of the shaft, okay? So we want to avoid this to happen, right? So in this case, when the shaft rotates, we have here, due to the practicalities of manufacturing and just the installment of shafts and the other components, there is kind of a center distance or eccentricity between two things. The first is the center of mass of the component or of the shaft and the center of rotation. The center of mass and the center of rotation. Let me just draw a very crude graph here. If, for example, we have a disc, and then this disc is carried on a shaft, okay? And at the beginning, it's like that. Then if this shaft starts to rotate, so I'm gonna say that at this point, this center here is the center of rotation. But when this shaft starts to rotate, what happens is that this desk is going to, let's say, it's a very crude, it's just very exaggerated picture, but let's say it's going to be like this. Okay, so then the distance between the center here and the center here is the eccentricity. Okay, so this eccentricity is, or the force, the force that is the centrifugal force here, is function of this of the omega of the shaft and function of this value E as well. Okay, so this is how you think about it. So let me just clear this first, and then let's go through this. So in fact, due to the practicalities of manufacturing and operation, the center of mass of this desk, or if you just consider that you are talking about the shaft now. So if we have a shaft, and then for this shaft, if this is, if we consider that it has a circular cross-section, and for this nice circle, it has a specific center. But due to the distribution of the mass here, due to the manufacturing, they have the center of mass somewhere here. So we have the center of rotation, this is the green guy, and then we have the center of mass due to the distribution of mass, and then there is a difference between them, that is the eccentricity, right? So when the shaft rotates, due to this difference between the center of mass and the center of rotation, so there is a force. This force is F, the centrifugal force, right? So as the shaft rotating speed increased, this centrifugal force increases as well, or tries to bend the shaft. So if we have bearing here, we have bearing here, so this shaft is going to bend. So what I'm drawing now is the center line. So the center line is going to bow, is going to deflect, okay? So the more speed, so the more the deflection, and the larger the centrifugal force. Again, what's wrong with that? So below the lowest or the fundamental critical speed, so there is a balance between the centrifugal force that is developed due to this eccentricity and the elastic forces of the shaft. So if we consider the shaft as, for example, a spring, okay, or a spring mass system. So in this case, when the speed, that the rotating speed is below this critical speed that we are talking about, the centrifugal force and the forces, the elastic force due to the elasticity of the shaft, they are balanced. And then there is a finite shaft deflection. The value of the deflection is finite and within range. But at the critical speed, if the shaft, if n is equal to n critical, which is the critical speed, this case, theoretically, this condition requires infinite displacement, or infinite displacement of the mass center, or infinite deflection, okay? So, but due to damping in the bearings, due to the windage, and due to the internal hysteresis of the rotating member, due to the internal hysteresis in the material, or damping inside the material of the shaft, this equilibrium causes a finite displacement. But the problem with this finite displacement this time, when we have the critical speed, is that this displacement is quite large. It is quite large to this in the sense that it can produce destructive magnitude. So the magnitude of deformation or deflection in this case is quite large. It can break the bearings. It can bend the shaft itself. It can go beyond the yield strength of the material, and so on. Okay, so but if we go beyond this critical speed, if the rotation speed or the rotating speed of the shaft goes beyond this critical speed, so again, we go back to something similar to case one, where the center of mass and the center of rotation, they go toward each other. So the most critical one, or the most dangerous one, is this one, when both the critical or the rotating shaft speed is equal to the critical speed, the deflection becomes very high, and therefore the displacement becomes, or the deflection becomes very high, and it's quite dangerous. So we want here to make sure that our rotating speed is less than the critical speed. This is what we are trying to do. Okay, so the critical speed is numerically the same as the lateral natural frequency of vibration. So if we kind of assume that we can model the shaft as a spring mass system, okay, and the shaft has a specific stiffness and specific mass. If you deflect this mass without rotation, you deflect this mass to a specific distance and leave it so it starts to vibrate. And then this is called the lateral natural frequency of vibration, where the natural frequency of this system is defined as K divided by M. Okay. So this is just a mathematical model of the shaft. So in this case, we can, based on this lateral vibration or natural frequency, we can find the value of the critical speed. Okay, so we'll learn more about this on the next few slides. But it is worth mentioning also that if you have a continuous system, so for this continuous system, I mean, for example, this is the ideal case. You have one mass and you have a massless shaft. So this is the mass, and then you have a massless shaft. And then in this case, you can consider this mass as a linear spring, and then these two cases are related. So this here is the mathematical model of this. But if you have a continuous mass where you have the mass is distributed across the length. So, sorry, let me just go back for a second to this. So in this case, we have only one critical speed. But if you have a continuous shaft like this with a distributed mass, so you have more than one critical speed. But the one that we are going to focus on all the time is called the minimum critical speed, the minimum critical speed. And then we want our operating speed to be less than this minimum critical speed. So this is the minimum or the fundamental critical speed. So the table here shows some cases. You have A, B, C, 3 cases. And the first case is similar to the one that I have just shown you. If you have a single mass with a massless shaft, so this is a massless shaft, and then you consider the shaft as a linear spring, and then you have, due to the rotation here, so there is some sort of deflection, and the deflection in this case is labeled as delta static. Then we can calculate here the lateral natural frequency, which is omega sub n, which is equal to the square root of k divided by m. There is some derivation that eventually tells you that in this case, the natural frequency is equal to root g divided by delta static. So delta static here means that you go back to, for example, let me just go back to this slide for a moment. You see here, we've just calculated Y max from this slide. So it is the same. So this Y max is the delta static that we are talking about. It is the maximum deflection in the center of the shaft, and this is kind of the same thing. So delta static here means the deflection that you calculate based on static loads. And then once you, so G is known and delta static can be calculated based on those theories, then the critical speed NC here is equal to 30 over pi multiplied by root G over delta static. So if you know delta static, you can calculate the critical speed. But what if you have, for example, different masses? Let's say the top one here, you have a single gear and the weight of the gear is high or big compared to the weight of the shaft. So this could be the ideal case. But what if we have like different gears on the same shaft or different components on the same shaft? So we can then use what's called the Rayleigh's method, where you have here mass 1, then mass 2, mass 3, mass 4, and so on. So, and then you can use these two equations to calculate the natural frequency and, to calculate the critical speed. So the idea here is that we use the superposition method. So the superposition method means that we are going to consider one mass at a time. So for example, you just consider that you have a single mass, which is M1, for example, here. Okay. And then this is M1. And then you need to calculate, in this case, considering that we have only M1, we have to calculate the value here of delta 1 and the value for delta 2, and then the deflection at delta 3. Okay, so based on only a single mass. So again, if I go back to this slide, if I go back to this slide and consider this case, look at this case, you have here one force or one mass at a specific distance. It's not in the middle. So you can use this these equations to find the Y max value. Then going back here, so you consider M1 first, okay? And then calculate delta 1, delta 2, delta 3. And then the next, you consider that you have M2 only. And then again, you find delta 1, delta 2, delta 3. And then the third, you consider that you have delta 3 only. And then you find delta 1, delta 2, delta 3. You can give them different names. And then eventually, delta 1 total is equal to delta 1, 1 plus delta 2, delta 1, 2 plus delta 1, 3. You say, for example, this is delta 1, 1 is the deflection when we consider M1 only. Then delta 1, 2 is the deflection at 1 when we consider 2 only. And then delta 1, 3 is the deflection when we consider 3 only, or the mass 3 only. And then this is the delta 1 total. Then going back to the equation, you see here delta 1. So this is the delta 1 total that I'm talking about. And then again, you can consider delta 2, delta 3, the total value of delta 1, 2, and 3, based on superposition. So you consider one mass at a time, and then you calculate the deflection at each point. And then if you have three masses, it means that you have three different deflections at each point, and then you add them together, and this gives you the total deflection at each and every point, okay? So this is the whole idea. And then you go back here, and then you substitute into this equation to find the critical speed. The same can happen if you have something like this. Let me just get rid of these to make it clear here. So if you have a shaft, okay, and then the shaft has different steps, you see, and then it has different sections. So you can again just subdivide the shaft into masses. For example, here this portion here has been divided into mass 1 and mass 2 equally. So, and then you have here mass 3 and mass 4. So you can just, you see the division line here. And then this is mass 4. And then you can again do the same, just calculate the deflection at each point, taking one mass at a time, and then add all the deflections together, and then substitute into this equation to find the critical speed. If you have the shaft mass only, you have a distributed mass, so you can calculate delta static in the middle based on this equation here that contains W, which is the linear load, which is the mass per unit length. L is the length of the shaft. E is the elastic modulus, and I is the moment of area. And then here you can calculate the natural frequency and also the static deflection. And then based on that, again, you can just simply calculate the NC. You know that, remember that omega is equal to 2 pi n over 60, right? So this is kind of the relation between omega and n. So if you calculate omega from here, you can calculate n from here. That's why you see here this 30 over pi, because if you just, if you divide this is by 2, divide this is by 2, it gives you 30 here. So that's why we have this 30 by pi, okay? So this table gives you all the symbols that we have seen on the previous slide and all the units. Normally we use the SI units, okay? Then there is one more equation. It is Dunkerley's equation. And what happens here, it's kind of similar to what we have done with the Rayleigh's method. Okay, it's just kind of similar, but another approach. So what they do here, what this equation does is that you need to calculate the critical speed NC using the critical speed NI on the shaft with only one mass at a time, right? So what you need to do, just again, consider that, for example, if you have three masses, so you consider your shaft, okay, with the first mass only. Then consider the shaft with the second mass only. Then you consider the shaft with the third mass only, okay? Then for each and every case here, you have a single mass, right? So it just means that you can go back here, and then we need to use the first equation. But for the first equation, we need to calculate delta static differently, because delta static here, not, for these three cases, not in the middle. So eventually the NC is equal to 30 over pi times root G over sigma stifler, sorry. So NC here is equal to 30 over pi times root G over delta static, okay? So what I'm trying to say is that delta static is calculated here. So this is delta static 1. Then delta static is calculated here. This is delta static 2. And then delta static 3 is calculated here. And then this means that you have delta static 1, 2, and 3 here. And then consequently, you have n critical 1, 2, and 3 here. So you have three values for n critical. If you have three masses, and then you go back to this equation and then substitute N1, N2, and N3 that you've calculated based on these three delta static values when you consider these cases 1, 2, 3, and then simply you can find the critical speed. Okay. Also, you can find the natural frequency, and the critical speed is measured in RPM, and the natural frequency is measured in radians per second. So there is one more equation you can use if you here when the critical speed of the shaft is unacceptable. What do you mean? So in this case, I said that we have N. This is the operating speed, right? Okay. So and this N operating speed has to be less than the N critical. Okay. So let me just give an example here. Let's say you've just calculated diameter, and this based on this diameter, you have the N critical as 2000 RPM. I'll call this all. Okay. Then in this case, the operating speed that you have based on the engine is 3000 RPM. Okay. So you see here that N is not less than N critical. N critical is smaller. So this is N critical in this case, N critical old. So in this case, we need to find another diameter. We need to find the new diameter that makes sure that this operating speed that we cannot change, so this is fixed, we cannot change, is less than the value of the N critical. So what we have here, we can say, okay, I want the N critical to be higher than 3000. I can assume that, okay, what if I have the N critical as 4000? So I assume that this is 4000 is higher than my operating speed. So in this case, I have the N critical new. But I don't have this diameter here. So what I do here, I go back to this equation and say the new diameter that I want is equal to the old diameter that I have already used to find this critical speed. And this diameter is coming from our previous design. We have design already, and we have a specific diameter based on stresses and everything. So this diameter, when I use it to calculate the N critical speed, so it gives me 2000. So I have the old value for critical speed. I have the new value for critical speed. And this value is informed by my operation speed here, or operating speed, sorry. So this can give me the new diameter. So I can calculate the new diameter that gives me, or just makes sure that my operating speed is less than my critical speed. But this is only happens when you have unacceptable value, okay?